Hello everyone, I'm Nasiruddin. Today we are performing a deep dive analysis on the frequency response of a passive electrical network. Specifically, we are looking at this fourth order high pass LC ladder filter. In computer engineering, these networks are essential for isolating high frequency signals while suppressing the lower frequency interference. Our objective is to mathematically model this system by finding its transfer function, Hs, which defines the relationship between our output and input voltages. To make this analysis manageable, we are working with normalized component values where every inductor is 1 Henry and every capacitor is 1 Farad. Our first critical step is moving from the time domain into the S domain or the Laplace domain. Here, the physical components are replaced by their complex impedances. The capacitors become 1 over S and the inductors become denoted by the variable S. This transformation turns our differential equations into simplified algebraic expressions, allowing us to treat the circuits as a series of voltage dividers. The ladder structure of this circuit requires a specific systematic approach. We will start from the load side and work our way back to the source. This involves calculating the series combination of the final branch, finding the parallel impedance at the middle node, and eventually determining the total input impedance as seen by V1. By treating the circuit as a cascaded system, we can apply the voltage divider rule multiple times to find how the signal tapers from the input to the output. By the end of this presentation, we will arrive at a final expression, a ratio of polynomials in the S domain that completely characterizes the behavior of this LTI system. Specifically, we will see why the numerator S4 confirms this as a strictly high-pass filter. Thank you very much.
Okay, so this is the circuit we have. This circuit is a physical circuit. And to solve this, we need to move to the mathematical mode. Move to the mathematical mode in the sense that we are transforming it from the time domain to the S domain. The reason why we are transforming from the time domain to the S domain is because in the time domain, capacitors and inductors are characterized by differential equation. And in using differential equation, this whole thing becomes complex and more complicated to be solved. That is why we have to move to the S domain, which is characterized by complex frequencies. So this is crucial because capacitors and inductors are frequency-dependent devices, and as you can see from here, the capacitors are connected in a signal path, and then the inductors are connected to the ground, which makes this a high-frequency pass filter. Yeah. So that is why we are converting to the S domain. And when we come to the S domain, we know that the impedance of the capacitor is given as 1 over C times S. And then the impedance of the inductor is given as L times S, where C represents capacitance and L represents inductance. So from the question we were given, the parameters were given as 1 farad, and then the inductance was given as 1 Henry. Inputting this into this equation, we can have the impedance of the capacitance as 1 over S and the impedance of the inductance as S. Inputting that into our circuits, that is changing the parameters we have here to the ones we finally found here. This is our circuit we'll be dealing with. Thank you.
So in this step, we'll be using nodal analysis to find for V2 and VA. We'll apply Kirchhoff's current laws at the two principal nodes, which are V2 and VA. So at node V2, the sum of currents leaving V2 must be equal to 0. And then we multiply through by 1 over x in order to simplify it. So after simplifying, we get x into brackets V2 minus VA plus V2 over x, which will be equal to 0. And then we multiply this equation by x in order to make VA the subject for the next one. So making VA the subject, we get x squared plus 1 all over x squared multiplied by V2. So then we go to the second node VA. So the sum of currents leaving VA must be equal to 0. And then we multiply through by x. Multiplying through by x, we get our equation to be into brackets 2s squared plus 1 all multiplied by VA minus s squared V2, which will be equal to s squared V1.
Now that we've been able to set up our S domain equation for the first node, we are moving on to the second node, which is V2 here. At this node, we'll be considering the voltage across the final inductor, which is our output signal. So when we apply Kirchhoff's current law, we see that the current has two parts over here. It passes through this capacitor and then it passes through here. And as we are aware, through KCL, current entering a node is equal to current leaving. So, but first we need to find the current through this part and then also this part. By using nodal analysis, we know that the difference in voltages at the nodes over the impedance will give us the current here. But what's the impedance? The impedance here is what we established here. So it will be 1 over S. And then when you do your math, you get S V2 minus V1. That's the current here. Then the current here will just be the voltage over the impedance, which is V2 on S.
Okay, so now we have to find the total current in the second loop, which is the current in the conductor. The capacitor is in the current in the inductor. This is the current in the capacitor and then the current in the inductor. We are just going to sum them. And according to KCL, the sum of the current in the second loop is equal to 0. So we equate the sum to 0. And then we multiply through by S in order to make VA the subject. So solving it algebraically, we will reach somewhere here, which we have to make VA the subject. So we just divide through the equation by S squared so that we can make VA stand alone. And so we factorize out V2 over here, and finally we have VA is equal to S plus 1 V2 all over S, and that's the final equation for VA. Thank you.
My name is Daniel Dromo, and my role is to solve the equations and obtain the transfer function. So from the previous step, we found that VA is equal to S squared plus 1 over S squared, all times V2. So I'll substitute the expression directly into the main node equation. So we have a fraction now, so to simplify it, I'll multiply the entire equation by S squared. So I'll multiply it by S squared, multiply every term on both sides so that the equation will be balanced. When I do that, the denominator will cancel, that is the S squared, and then we'll be left with 2S squared plus 1 in brackets, S squared plus 1 in brackets times V2 minus S raised to the power 4 times V2 is equal to S raised to the power 4 times V1. Then I'll expand the brackets. So then if I multiply it out, it will give me 2S raised to the power 4 plus 3S raised to the power 2 plus 1. Then I'll combine like terms like the 2S raised to the power 4 minus the S raised to the power 4 is just S raised to the power 4. So then the equation now becomes S raised to the power 4 plus 3 S raised to the power 2 plus 1 times V2 is equal to S raised to the power 4 times V1. Then when I divide both sides by V1, I get the transfer function, which is HS is equal to S raised to the power 4 over S raised to the power 4 plus 3 S raised to the power 2 plus 1.
So we have two equations after deducing the circuit, equation 1 and equation 2. But equation 1 has VB, equation 2 also has VB, so we can relate both equations. It's basically change of subjects we are going to do over here. We have VB being equal to V1 multiplying S squared, bracket open, 1 plus S squared, all on 1 plus 3S squared plus S to the power 4. That's equation 1. Then the other equation, VB being equal to V0 bracket open 1 plus S squared, all on S squared. Now we can equate both equations. Get V1 of Yeah, so vi bracket open s squared 1 plus s squared over 1 plus 3 s squared plus s to the power 4 being equal to v naught 1 plus s squared all over s squared. Now since we want v naught on v in, we try and make it a subject, so we will get v naught over v in multiplying 1 plus s squared over s squared being equal to s squared bracket open 1 plus s squared all on 1 plus 3 s squared plus s to the power 4. Yes, so now we can do some change of subjects here, or change of subjects here. So we get v naught over v in being equal to s squared times s squared multiplying 1 plus s squared all over 1 plus s squared multiplying 1 plus 3 s squared plus s to the power 4. Okay, so as we do cancellations, 1 plus s squared cancel 1 plus s squared and s squared times s squared, the power with the rule of indices, we get s to the power 4 all over 1 plus 3 s squared plus s to the power 4. That will give us our transfer function v naught over v in.
Hi, I'm Godson, and we'll be reviewing the transfer function that was solved at the end of everything. Yes, so at the end of solving the equation in the time domain and transferring to the Laplace form, we had a transfer function being s to the power 4 out of s to the power 4 plus 3s squared plus 1. Yes, and we want to review the behavior of the filter or the circuit when various frequencies are passed through the circuit. Yes, so at low frequencies where s is approaching 0, or yes, when the frequencies keep reducing and approaching 0, by substitution we realize that the output is almost nearly 0 or even 0 because the circuit tends to block all low frequencies that are passing through it. Then also at high frequencies, we consider the s value with the highest power. Yes, and in the equation we realize that s to the power 4 is the highest, and so we go in for that one. And so taking those ones out and bringing it down here, we have s cancelling s out, giving us a value of 1, which means that the input voltage is going to be equal to the output voltage at the end of everything, and we can deduce from this that the circuit is a high pass filter. Thank you.